Well, greetings everybody. I want to talk about roots in general in this video, and in particular I want to talk about how you can reduce roots if they're not perfect. Okay, so in part one of what I have here, every root that you see in this column, numbers 1 through 7, we could all say these are perfect. Okay, and I'll explain what I mean by them being perfect. Alright, take for example square root of 49 being 7. The reason why I say this is a perfect root, square root of 49, is because there is a whole number, 7, such that 7 squared is 49. Okay, so that's why we say square root of 49 is equal to 7. You could also, if you want to generalize this initial idea I'm telling you, you could think about it like this. If I had the n root of some number a, and I said it had to be equal to b, then what I would mean by that is that if you took this number b and you raised it to the n power, you would get that number a in there. That's how roots work, okay? And that's how I could justify or know that any answer is correct if this happened. Now here in square root of 49, that index right there is a 2, right? So we might write down square root of 49, but the root that we're talking about that's unwritten is a 2, okay? So that's why I say that, okay, the reason why I know square root of 49 is 7 is because if I take 7 and I raise it to the second power, which is the number that's understood to be the index of that root, I will get 49. Okay, there's a whole number that does that. That's why I say it's perfect. Now all of these are perfect, but let's run through them real quick and then we'll see if we can figure out this last one ourselves. Okay, why is the square root of 81 equal to 9? Because 9 squared is equal to 81. Why is the third root of 8 equal to 2? Well, remember that pattern up here that I said holds for all roots? If you take 2 and you raise it to the third power, you will in fact get 8. That's why I know the answer is 2. Cube root of 64 or third root of 64 is 4. For the same reason, 4 to the third power is 64. The fourth root of 16 is 2 because 2 to the fourth power is 16. The fourth root of 625 is 5 because, you guessed it, 5 to the fourth power turns out to be 625. Okay? Alright, well, so what do you think about this last one? I left this last one open for us so we could figure this one out. What's the fourth root of 81? Well, how about, since I'm looking for what number, if I raised it to the fourth power, is equal to 81, I'll just go down the list until I find it. What's 1 to the fourth power? That would be 1 times 1 times 1 times 1. That's just 1. What's 2 to the fourth power? Go 2 times 2 times 5. Multiply all that out. 2 times 2 times 2 times 2. I'll get 16. So do you see how, like, maybe if I keep going, I'll be able to find it? What's 3 to the fourth power? If I calculate 3 times 3 times 3 times 3, I will get 81. Okay? So the answer is 3. So that's how I can find it. All right. Now, that's the basic idea behind roots, and that's how they're understood, and that's how we can know that any one of these problems is correct. Okay. Now, as you're watching this, you might be thinking I'm leaving an important part out, or I'm making this too difficult. Why can't we just do this with a calculator? And you can do this with a calculator. I think you should know how to do this with a calculator. Calculator is an important tool. It makes things easier for us. Nothing wrong with using a calculator to its full ability, but I would be uneasy if somebody claimed to be good at math or worked in a field where they were supposed to be knowledgeable about math and they had no idea where the number from the calculator came from. It's fine to use it, but I think you should understand what's going on as well. So, of course, we could take a calculator and we could do that first question, square root of 49 is equal to, what do we say? 7 And of course it tells me 7. So yeah, you could use a calculator if you want to. Your calculator could even do higher roots, I'm sure, like third root of 64. Here's how I would have to input that on my calculator. Now, every calculator might have a different syntax to it, a different way of typing things in, but if I wanted to do third root of 64 on this calculator that I have here, that's how I would input it. And I can't really give general advice. There it is, third root of 64 is 4. That's the answer we came up with. I can't give general advice on calculator use because the buttons and the syntax is different on most calculators. Okay, so these are the easy examples. These are the perfect roots. Every answer to each of these problems is a whole number. Now, let's go to part 2 where what about these? Like, what about square root of 50? There isn't a whole number that if you square it, you get 50. And that's what the square root of 50 would be, okay? I mean, if you wanted to go through a little trial and error, we could say, well, 6 squared is 36, okay? 6 squared is not 50, so that's not the answer. 7 squared is 49. 49 is not 50, so that's not the answer. So you see how it's like I could just go down the list and I could try to find the number that you square to get 50. 8 squared is 64. So see, I went from 6 to 7 to 8, and it skips over 50. There's no whole number that if you squared it would give you 50. So how can these be reduced? Is there anything that we can say about these? We'd like to reduce them. We'd like to give some kind of answer. In math, like if we take whatever we have and we generally want to reduce it down to its simplest, most basic form. And that's what I'm wondering if we could do that here with these. All of these are not perfect, okay? So let's see. There is a method for doing this, and my opinion on the method most of the times in math is if I just explain the method, it makes it seem harder than it is. If I just showed you how to solve these problems, I think you'd probably pick up on the method yourself, just if you saw enough examples. But still at the same time, I think I should outline the method. So here's the method for reducing non-perfect roots. Say you have the in root of some number k, okay? And that's kind of like root 50, where there's no whole number that's an answer to that. Then here's what we do. We factor the number k. Now this is like a factor tree right here. It's kind of like saying the number 25 factors as 5 times 5. Okay? Or it's like saying the number 50 factors as 25 times 2. Something like that. Okay? That's what I mean here. It's a factor tree. So we factor the number k as a times b. Some number a times some number b. But we find this first number a to be the largest perfect in root of the number k. All right? So I'll show you what I mean by that through the examples. So we take k, we factor it into a times b, where a is a perfect in root. Okay, by perfect I mean it works out kind of like these first examples, like square root of 49 is 7. That one's perfect. Okay. And then there's this property of roots where we're allowed to split those apart and work each of them individually. This first one, because it is chosen to be perfect, will reduce. So we reduce that one. This other one won't be, and we'll just have to leave it alone. Okay. All right. Now that's an outline of the method. Like I said, I think it's hard to learn it just from the outline, but there it is. I'll work the examples and show you what I mean by the outline. So root 50, okay, so 50 is not a perfect square. So can I factor 50 in a way that there is a number that is a perfect square factor? Okay, so with 50, I could factor as 25 times 2. and 25 is a perfect square. In fact, of all the factors of 50, 25 is the largest perfect square root of 50. Okay? There are other ways you could factor 50. You could factor 50 as 5 times 10, but 5 is not a perfect square, and neither is 10, so that won't do any good. All right? So here's what we'll do. We'll say, okay, I got 50. 50 factors as 25 times 2. Okay? And then we're allowed to work each of those individually, meaning that this becomes root 25 times root 2. Okay? Now, from there, I can tell you what root 25 is. That's a perfect square. Square root of 25 is 5. What about square root of 2? It's not a perfect square, and it's not further reducible. Okay? Because remember, you choose this number a to be the largest number that is a perfect in root. You reduce that one, and you leave the other one alone. So we'll have to leave alone the root 2. So we'll get 5 root 2. Okay, there's our answer to that one. That's how we can reduce it. Okay? Let's try root 32. Same way. So we take 32, and I want to factor it in a way that I get the largest perfect square factor out of it. So I could say 4 times 8 if I wanted to. 4 times 8 is 32, but 4 is not the largest perfect square factor of 32. Okay, so what are your perfect squares? Perfect squares are 4, which is 2 squared, 9, which is 3 squared, 16, which is 4 squared, 25. You see how the list goes on like that. 4 is a factor of 32, and it is a perfect square. But it's not the largest one. 16 is the largest perfect square factor of 32. That's the one we should choose, okay? I mean, once you get beyond 16, like 25 is too big, and it's not a factor of 32 anyway. All right, so let's do this. We want to do 32 is 16 times 2. All right, and then the breakdown will be like this. Root 16 times 2. Okay, 32 is in fact 16 times 2. No problem there. Now I work these individually. Root 16 times root 2, because you can split them apart. And 16 is a perfect square. The square root of 16 is 4. So this is 4 times the square root of 2. And that's as much as we can reduce it. All right. So let's see if we can apply this to the other higher roots. We got third roots here, fourth roots there. Let's try it out. Okay. So let's see, 16, and I want the third root. Okay. Now I need to factor it in a way that I get the largest perfect third root out of it. Okay, so there are lots of ways to factor 16. I could say 4 times 4, but that won't help us here because 4 is not a perfect third root. Okay, it might be true that 16 is 4 times 4, but it won't help us. All right, so can you factor 16 with a number that's a perfect third root? So what are perfect third roots? So there's 2 to the third power is 8. There's 4 to the third power, which is 64. Okay. And already I see 8. 8 will work. 8's a factor of 16, and 8's a perfect third power. All right, so that's what we want. So let's say 8 times 2. Okay. All right, so I can just go down the list until I find the number that is 1 a factor of 16 and 2 is a perfect third root. So look what I do next. So I'd say, okay, 16. 16 is, as a matter of fact, 8 times 2. But now I can split this up. This is the third root of 8 separately times the third root of 2. And I can tell you what the third root of 8 is. The third root of 8 is a perfect cube, perfect third root. It's 2. So I get 2 times the third root of 2. Okay? Third root of 8 is 2. And remember, I'm going to have to leave this other one alone. So long as you choose this number to be the largest number that's a perfect root, then this one will be irreducible beyond that. So I'm going to get 2 times the third root of 2. That'll be my final answer. I can't reduce it down any more than that. Okay? So let's try third root of 128. So let's take the same strategy. I'm trying to factor 128. And I'm going to do that with numbers that are perfect third roots. Okay, so what are those again? 2 to the third power, that's equal to 8. 3 to the third power, that's equal to 27. 4 to the third power, that's equal to 64. Okay, 5 to the third power, that's equal to 125. So now we're getting too big. Like a number like 125 is not going to be a factor of 128. So what we do is choose this one, 4 to the third, 64. 64 is a factor of 128. All right? Okay, so I want to do this. I want to do 64 times 2. 64 times 2. 64 is a perfect third root. Okay, no big deal there. And multiply by 2, you get 128. All right, so we'll get third root of 64 and times 2. And then they split apart, right, into third root of 64, which is 4. Okay, 4 to the third power is 64, so third root of 64 is 4, times the third root of 2. Okay, and then there's our answer to that one. All right, now so far you might think, well, all these look like it's just a 2. Can you just divide by 2 every time? Like, see, like 50 is 2 times 25, and 32 is 2 times 16, and 16 is 2 times 8. It's like, well, I mean, that's how these have worked out so far. Doesn't mean all of them will work that way. Let's look at 162 right here, fourth root of 162. All right, so my strategy. I'm going to look at the number 162. I'm going to try to factor it with the largest fourth root, the perfect fourth root that I can. Okay, so what are perfect fourth roots? 2 to the fourth power, that's 16. 3 to the fourth power, that's 81. Okay, 4 to the fourth power, 256. Okay, all right. So, well, it looks like 256 is too big, right? Okay, can't be that one. 81, is 81 a factor of 162? I'd say yeah. It's like 81 times 2 is 162. So we get fourth root of 81 times 2. All right, 2 times 81, that is in fact 162, but 81 is a perfect fourth root. Fourth root of 81 is 3. So working these individually, fourth root of 81 is 3. And then I got fourth root of 2 that's just left over and can't be reduced any further. Okay. All right, so like I said, they've all been factored with a 2 so far. Maybe that's the way it will happen a lot of the times with the problems that you see on the homework, but I can't guarantee it. Let's look at this last one. So fourth root of 48. All right, so you know the technique by now. Maybe you could even practice along with me. Okay, so 48. All right, I need to factor 48 in a way that has the largest perfect fourth root in it. Okay. Now, all right, if I went through the list again, 2 to the fourth power is 16. 3 to the fourth power is 81, and already 81 is too big, so I guess we can only look at 16 this time. So let's say 16 times what? Is 16 times something equal to 48? 16 times 3 is equal to 48. Okay, so 16 times 3 is 48, so that would be correct, but 16 is a perfect fourth root. The fourth root of 16 is 2. All right, that's what I want this time. Okay, so all right, let's say what we reduce this one to is fourth root of 16 times 3. Okay, and then as with my first 3 problems, I can apply this root to those numbers individually. This would be fourth root of 16 times fourth root of 3. Fourth root of 16 is equal to 2. And so we'd say 2 times fourth root of 3. 2 times fourth root of 3. Okay, this last one will be irreducible so long as you factor this in a way that that number is the largest perfect fourth root of 48. Okay? All right, so that's how we reduce the non-perfect ones. We factor, we choose a number that's a perfect root of whatever we're dealing with, and then we break into parts. We'll be able to reduce the first one, and we'll leave the other one the way that it is. That's the way it works. Okay? So you'll encounter 2 types of roots. You know, the ones like these that are perfect, and you get a nice whole number every time, and the ones like these that aren't, and we'll take some factoring in the way that I've described here. Okay? Now, it might even be, as you're watching this, you might think, you know, can't we just do this on calculator? And my answer to that's maybe. Some calculators will reduce roots like this. If you put in root 50, it'll tell you it's 5 root 2. That's okay. It's not like I'm opposed to using a calculator, but I think as a STEM student, as somebody who's possibly going to do something technical and highly mathematical, I think that you should know how to use the calculator for sure. But you should know where those numbers come from in addition to that. I'd like you to know it all. I'd like you to know the technology, and I'd like you to know how you do things on paper with your own brain. Okay, so mental math is definitely not a bad thing if you're doing any kind of science or technology. All right, so those are the 2 types of problems. One more caveat about this is there any problems that could come up with using a calculator? Like, so say I take this problem right here, root 50, and I told you the answer was that it's 5 root 2. That's the reduced form. Okay, so if I use my calculator, let me show you what I get. Root 50, and it tells me this decimal that takes up the whole screen, 7.071067812. Okay, so could I say that that was the answer? At best, you could say root 50 was approximately equal to 7.07107 if you rounded it, or you could even write this whole number down. It would still only be an approximation. Square roots like this are called irrational numbers, and what that means is that you can never fully write down all the decimal places to the number. So that means no matter how many decimal places you write down, it's not exactly equal to whatever root 50 is. Okay? Now, scientists and engineers, and people that work in technical fields, have to work with approximations sometimes, and that's fine. Okay? But it would be wrong to state that root 50 was equal to 7.07107. That's not true. This is only an approximation. Even if you wrote down every one of these numbers on the screen, it still wouldn't be equal. Okay? You cannot write down enough decimal places to make this an equals. So when you use your calculator, you may get a number like that with so many decimal places, but it is only an approximation. They're not equal. The wavy lines right there, that is our approximation symbol in math. Don't put that they're equal. That wouldn't be correct because they're not equal. Okay, they might be very close, but they're not equal to each other. They're not the same number. So that's why as we do math and deal with roots sometimes, instead of using our calculator and getting decimal places, which are only approximations, they are not truly equal for roots like this, we'll reduce them in the way that you see here. Okay, So that's a little bit of a crash course on how you understand and reduce roots. If you took a basic algebra class, let's see, this video is 25 minutes long. You'd spend more than 25 minutes on it, but this will hopefully jog your memory a little bit if you've heard of this before. And even if you haven't, hopefully this is enough to understand the idea and be able to practice it a little bit as you encounter it in the assignments.